My mic is on. I've hit go live. Let's take 10 seconds to make sure I'm live. I can hear myself. Awesome. Wow, that's a large crowd to learn deep learning, especially on a theoretical book. Hey everyone, welcome to the study group. Let me take my headphones off. So this is something different to what I usually do, in the sense that this book, Deep Learning by, it's honestly by legends of the field, is one of the very popular books, with a very critical feedback, or one thing that has carried me for a long time, in the sense that I purchased this book in 2017, and since then I've not had the courage to touch it. And for reference, if you're just clicking on this video, we will learn linear algebra, but for the first 5 minutes I'll just set up the expectations and the general idea of what we'll be doing. So as I said, I had this near my shelf, and I was hoping some knowledge would distill into my brain by itself. Apparently it did not. And the reason for that is this book is very theory intense, and that's also one of its critical feedbacks, right, that the audience gives. So what we'll try to do in this study group, and this happens every Saturday, right? So if you're watching a recap, consider subscribing and you'll be notified for the next time when I actually do this. Or you can join me live. Yes, as I was just saying, that it is a weekly uh, study group. So every Saturday at 8 a.m. Pacific, I'll be live streaming this. But the plan is to cover every chapter in sequence. And what I've done is, if you check the description right now, the first link there would take you to a community repository. And what I want to achieve with us as a group here is, I want to fill this repository up with supplementary materials. And I've already created one notebook that I'll push to this repo after the live stream. But what I want us to do is, we can create a supplementary resource where you can actually learn and translate this knowledge to NumPy, and you can have supplementary questions, hopefully also apply this somewhere. So the reason why I say that is because this is a very theory intense book, right? So you learn all of these symbols, you learn all of these derivations, even in the first chapter. And where do you apply that? So the things to pay attention, at least for me, and hopefully for you as well, since you're joining me on a Saturday. I'm just a guy who will keep doing this in his room anyways. But if you're giving your time, might as well pay attention to the notations. Sorry, there's a fly here, which is very interested in deep learning. Um, Pay attention to the notations. And what I'll do is, I'll summarize every chapter. I'll actually screen share to the book, and we'll go through the book's chapters. I'll point out the important things, and make sure you translate that into code, right? Like, hopefully every one of us wants to apply this somewhere. So the like end goal for all of us, or for me and hopefully for you, will be to like, how do you read this chapter and see code when you read a paper with a capital A. So when you see a capital A, or when you see LP norm or L2 norm, whatever that means, which we'll learn in a second, how do you in your brain come up with like the particular NumPy function, for example, or the PyTorch function? So that's my goal for this study group. Hey Manshu, thanks for joining. And like I said, it's a live study group, so please feel free to leave anything you have in the chat. And usually I live stream about Kaggle and similar things, so this is something unusual for me as well. I'd be happy to be corrected. So if you find some explanation that's not accurate, please do mention that. For all discussions, we'll be using the H2O AI community, which also you can find a link to in the description. But what I require all of you to do is, please consider joining here and introducing yourself. So by the next live stream, I'll probably have a section for us to discuss and interact about math. Usually I don't do this because we can simply discuss things live and you don't need a separate area to do that. But I feel for math, and especially for a book like this, this can be actually helpful, because hopefully all of us will spend more time and interacting with each other about mathematical equations, which YouTube comments is in the right spot to discuss. So those were some housekeeping items. We'll meet every week. I'll live stream every Saturday. We'll go through each chapter every week. The next live stream is live already, so you can already get notified whenever that happens. And I'll try to convert as much of this theoretical knowledge into code as much as I can. Hey Shannon, hey Parth, thanks for joining. I'm excited to learn with everyone as well. So what I'll do now is I'll start giving an outline and I'll start going through individual concepts as I see important. Please ask as many questions as you want, or you can ask the question in the forums that I just pointed to. Again, all important links will be there in the description. And right after this lecture, I'll push this notebook to the repository that I've set up. And I'd love for you to also contribute to this. So my plan for this lecture is to cover everything this discusses in NumPy. Some people call it NumPy, and I don't understand why Python is not called Python. So for me, it's NumPy. And we'll learn how to translate all of these concepts into NumPy functions. Let me zoom in a bit. And I have just come up with this notebook. I saw someone's comment where they mentioned the lack of exercises. So this was basically cooked up in an hour, which means the final one will be slightly different and will have more text around it. So please excuse the lack of text. But here's the broad agenda. So we'll cover one chapter every week, just to reiterate. And hopefully I invite, or I'd strongly suggest everyone to and everyone's agreeing about Python not being called Python. So we've established today that it's NumPy and not NumPy. Send this video to anyone who disagrees. But anyways, so one thing I'd strongly encourage everyone is to either contribute to the repo or write blog posts, because again, we're not here to just read the book, right? Like I bought this in university, and at that point, this would have been a badge of honor that hey, I've read this book. But like the real stuff is converting this into knowledge and showcasing it somewhere. So consider writing blog posts, consider doing tweetathons. Tag me whenever you post them. I'd be happy to share them across. And like code as much as you can is what I'm trying to say. Thanks for joining. And please keep the chat coming. I'll keep an eye out for that. So these are the topics covered inside of this chapter. And for the first few ones, I'll spend more time in NumPy. For the last few ones, it's more of a theoretical definition. So I'll try to explain the definition. But at the end of the day, if I even scroll ahead a bit, ahead of time. So what I'm going to do is I'm going to show the definition of something. So here's like an entire page of how Eigen Decomposition works, and it's really good to know how it works, right? But in reality, the thing to pay attention once you know what it is, which is also important, is how do you calculate that in NumPy? And please excuse the crazy scrolling. But how you do that is just by calling a function inside NP linear algebra. So make sure you spend time exploring this np.linear where you'll find most of these functions. But realistically, this takes care of everything. So that's what you should be paying attention to. So you should know how this comes around, and you should have a, for me, this is how I would go about the book. I'd have a vague understanding of how eigenvalues work. We'll come to that. I'm just giving an overview. But what I'd really love to remember is how do I do that in NumPy, and how do I do that in PyTorch. PyTorch is my preferred framework for deep learning. So for my, and as a suggestion for your expectations, I would suggest focus on that and spend as much time as you can in this Jupyter shell or VS Code. Run a Jupyter notebook inside a VS Code. Run a Vim inside a Jupyter notebook. I don't know what extensions come up these days, but do that as much as you can. So we'll be learning about what are scalars, vectors, and matrices. We'll be learning how to work with them. We'll be learning about special types of matrices and vectors, and a few more mathy terms. So we'll learn about norms, Eigen Decomposition, SVD, which is singular value decomposition, pseudo-inverse, trace and determinant. And the nice thing is, even if I copy anything from here and just look up NumPy, right, it should take me to the function. So instead, And this is again a strong, very strong suggestion from me. Instead of looking up, what's the exact word, uh, the exact word is slightly scary, so let me scroll to that. But instead of looking up what is the more pseudo inverse, just go to the numpy documentation and understand it through the example. I'm sure you'll understand it better through that, and that's what I've learned. So instead of looking up what pseudo inverse is and how it's done mathematically, just read through this, and this would, for me at least, this would make more sense. And as practitioners, we're supposed to spend more time in Python, right, than math. And for theory, I would say just pay attention to how the notations are written, because that's what really matters, right? So when you're reading through a paper, a to the power minus 1 means an inverse. And what is an inverse? We'll just learn that. So that's what you should be paying attention to. Again, I'll keep setting these and giving some strong opinions as I go about it. And let me close this tab now. So as a reminder, I would love if everyone would like to contribute to this repository. And the goal for me is to like create a NumPy supplement for this book, or a PyTorch supplement for this entire book, as you go about it through the weeks. So for the first few topics in the book, I'll cover them through the notebook, and then I'll start going to the book more and more as we get into the theory a bit. Um, if you're new here, or if you're not aware of the book, just go to deeplearningbook.org, and you can find all of these chapters for free here. There's no catch; the authors have genuinely made it available for free, so you can completely read it online. For me, I like studying with physical books, so I have a Kindle, but for such books, I like to buy the physical copy. You can also do that. Okay, so moving on with the basics. So for section 2.1 to 2.4, I'll cover them through NumPy. And Vadim is asking, will we cover dot product? Yes, we will. And I had a nice confusion there, which I'll also try to uncover, specific to dot product. So NumPy, if you go to the website, it'll give a nicer description, but everything related to matrices and vectors and tensors is usually done in NumPy. You could probably also do it in TensorFlow and PyTorch, which you should be when you're working with a large set of these, and especially when you're computing uh, matrix products and basically doing deep learning stuff, running neural networks. You should be using PyTorch, and you should be running your stuff on your graphic card. But NumPy is a nice compromise, because the APIs are very similar and the functions behave very in a very similar fashion. So we'll start here. And here what I've done is I've defined what is a scalar, what is a vector, and what is a matrix. So scalar is just a number. And I've used Python here. So I've defined a list with a single number 5. So a scalar is just a number 5. And you could also think of this as a vector with just one number. So what is a vector? A vector is a single row or a single column of a few numbers. For this example, it has 3 numbers, and it's a list of 3 numbers like so. You could also store a scalar like so, and it's still a scalar. It doesn't change into a vector, or it can always be a vector with just one number. And that's, I might be messing up the mathematical definition, but a vector with just one element can also be thought of a scalar. Matrix is a collection of a few vectors like so. So here we have two, you could think of them like row vectors, and they're basically stored in memory like so. You could think of it like that. And the like thing to remember here is, whenever you're thinking of memory storage, right, that's only a human representation and how you would understand it in your brain. These numbers are stored in a continuous array inside the memory. So it's not really that a matrix is represented in any different manner compared to a scalar inside the memory, except that it's stored in continuous blocks. But a matrix can be thought of two row vectors combined together. And a tensor is an even higher order matrix. So it goes into even higher dimension than that. That's a very vague definition, and that's not mathematically accurate at all. And what I'll do is I'll look inside the book and just spell out the exact definitions from here. You're welcome to read the chapters. I'll only glance over the important bits. So scalar is a single number. A vector is an array of numbers. A matrix is a 2D array of numbers. And tensors are arrays with more than two axes. So when you go into higher dimensions, it becomes a matrix. And again, same things written nicely can be thought of like so. But this just doesn't change anything really. It's only for your readability. It's the exact same thing in the memory. So for shapes, you can print out the shapes by calling dot shape. And I've converted these into arrays. So what I've done here is I've called numpy.np.array, which will convert all of these into basically a numpy multi-dimensional array. And then I printed the shape. So as you can see, a vector has only uh, three numbers inside of it, and it can be thought of a row vector here. Sorry, it'll be a column vector. Um, sorry, it'll be a row vector. Yes, it'll be a row vector. I'm getting confused, but since the first number denotes rows and the second denotes columns, it's row by columns, it's a row vector. A matrix has, this matrix especially has 2 by 3. So 2 rows and 3 columns. And the tensor has, it's in higher dimension with the shape 2, 2, 2. But when you actually print out the shape of their ranks, it's all one. So what is a rank? And what is a shape, what is a dimension? I leave that to you to explore inside numpy. And mathematically, again, the definition would be slightly different, but as you go about numpy, you'll always get confused initially what is rank, what is shape, and what is dimension. I would suggest that you spend some time trying to remember that, because it gets confusing really fast. And the thing to remember is numpy has, if you print out dir of np, you can see all of the functions inside of it. And I would encourage you to check out as many of these as you can. An interesting reason to call it a scalar: when you multiply a vector with a number, you are scaling it. Hence, that number is scalar. Yes, I think this was inside the book, and thanks for pointing that out. But yeah, so in essence, a matrix represents how distant numbers are from the origin, and you are scaling that distance whenever you do that. Like Ishan said. Thanks, Ishan. Yes, this will be available to watch later. It's not a lecture, it's only a study group. Some conventions and how to access these examples. So, one thing to remember: a capital A, the flies back to learn deep learning, sorry. The matrices and tensors are represented with capital A's, and I comma j usually denotes their example in the ith row and jth column. So let's do this. What I've done here is I've created one array A with examples from 0 to 11, and it's in a shape 3 comma 4. So when I'm accessing 2 comma 3, and note this would mean 3 comma 4 because numpy and python are 0 in text, but I'm accessing the fourth number in the third row. So 1 2 3 4 in the third row, that would be 11. But since we're working inside python, not python, this would be a2 comma 3, and that would print out 11. So that's how you access numbers inside a matrix, and that's the general notation. In math, these are usually subscripts, so the I comma j can be written under a. In python or in numpy, they're written like so. So 2 comma 3 is I comma j, and that brings us the number in the ith row and jth column. When you put a colon, not a semicolon, a colon, uh, you are selecting the entirety of that axis. So a row could be an axis, a column could be an axis, but what we're telling here is, hey numpy, please select the entire fourth column. Why fourth? Because again, this is 0, 1, 2, 3, which is the fourth column. So this should print 3, 7, 11. So we end up selecting this entire column. You could do the same for a row. So instead, if you switch, let's say like so, this should print the entire third row. So you'll have 8, 9, 10, 11. And when you actually do this, when you put inside exclamation, colon, comma, colon, this would end up printing the entire array. And if you skip giving a number to numpy, it basically selects the entire thing. So you would still get the entire array if you try to subset like this. And when you subset like so, you're getting the second row. So we're only selecting the second row when we do this. And if we say 0 here, it'll select the first number, 4. So that is how you access different numbers inside an array, and that's the general notation. So matrices and tensors are denoted by capital letters. So capital A would refer to a matrix or a tensor. Small letter would generally refer to a scalar or a vector. And a vector is just a single row or a single column collection of numbers. You could think of it like a Python list with a few numbers in it. The next section is doing matrix multiplication. So what I've done here is I've created a NP array like so, but I get an error which says it takes only 1 to 2 positional arguments, but 3 were given. So the thing to remember here is it only accepts lists, and then it converts list into a numpy array, sorry. Um, so when you actually pass a list to np.array, it'll create an array out of it. And same thing for B. And the general notation to perform multiplication is written like so. So in papers, AB basically means a multiplication, or A star B also means multiplication. But when you do that, it says it could not broadcast the shapes together. So maybe we look inside NumPy and we dig around. So you'd come up with np.matmul, right? And that does sound like matrix multiplication. When you look inside, it is actually the matrix product of two arrays, and that would give you the matrix product like so. You can also, so I'm covering the matrix operations. There's a question that says, how many sessions to finish the book? I think we'll have about 9 live streams or so. So the plan is to cover the first 10 chapters, and we're currently going through the second chapter. I assume from the next week I could do more than one chapter, but for the first one, since I've only created this incomplete notebook, I only wanted to do the first one. So when you try to add any array, you cannot, because their shapes need to be the same. You can add a scalar to a array, which means that you can do a plus a, and what this would mean is every element in a so let's say a is equal to 5, and when you do a plus a, every element in a would have a 5 added to it, and that is numpy at work. This is not something that's very common in math notations, but when you actually do that in numpy, it's possible because it just scales everything, and that's known as broadcasting. So what numpy would do, it will figure out that, hey, this is a number that's supposed to be added to this array, So it'll expand this into an array that's of the same size as A, and then it would basically add all the elements together. So if A was 1 comma 1, numpy will basically convert this into 5 comma 5, and A plus A would then become 6 comma 6, like so. So they need to be of the exact same shape. You can generally switch, or you can always switch the order when multiplying three matrices. So the multiplicative of A along with B C is equal to the multiplicate of AB followed by C. And what this means in notation is A into B star C is equal to A star B and C. You could skip the star, you could have the star. Some places it's in some notations it's included, in some it's skipped, but generally, and uh, I think generally it's usually skipped in notations. So it's good to have an idea that you're dealing with a matrix there. um you can take the transpose of a matrix like so, and it's denoted by A to the power T. When you actually call that, it simply prints a function. But the ideal way to print that would be np.transpose. So a transpose flips a matrix alongside its diagonal, or it rearranges the matrix like so. So the rows become the columns and the columns become the rows, in the sense that 1 comma 2 would become a column, 3 comma 4 would become a column, and 5 comma 6 would become a column. So as you can see, the first column is the first row, the second column is the second row, and the third column in the transpose is the third row. Now, one cool thing that I learned later on, and I said something incorrect earlier, which is what which claimed that np.maximal is the matrix multiplication. When you call np dot, which calculates the dot products of two arrays, it is the same as np.maximal, which means that the dot product and matrix multiplication is the same, which is not true, right? So what went wrong here? I thought maybe if I create, maybe I got lucky with the initialization. So let's create two random, absolutely random arrays and see if it works. It still did work. So it gave me true for all the elements, and it's the claim here is the dot product is same as np.maximal. So later on, I learned the correct way to do that would be through np.multiply. So when you call np.multiply, that actually returns you the matrix multiplication of the two arrays. How do you calculate that? That'll require me to switch to my OneNote tab here and bring up my pen like so. So let's say these are the two arrays that I'm working with: 1, 2, 3, 4, 5, 6. This would be a 2 by 3 matrix. It has two rows and three columns. And let's say I have 1, 2, and 3. This would be a 3 row by 1 column. So what is being done in the final product is that every row will be multiplied by every column, and the same later on. So the number here would be the sum of the multiplicators of this row with this column, and same here. So this would give me x by y, where x would be um, summation of the first row of this matrix and the summation of this multiplicative summation. So I should write this as pi actually. Sorry about that. But basically, this row multiplied by this entire column. One thing to note here, the final shape here becomes 2 by 1. And what's going on here is the first number from here and the second number from here becomes the shape of the multiplicative of these two. So that's how you do matrix multiplication. If you do it by hand, it'll get frustrating after you surpass 3 by 3 matrices. So I would challenge you to do it for 6 by 6 and let's say 6 by 7 matrix. You'll get quite frustrated. So the ideal thing to do here is call np.multiply. And the reason I wanted to point out the shape thing, when you try to multiply any array with any array, that's not usually possible because their shapes, as I mentioned, should be compatible in the sense that if A has a shape of x by y and B has a shape of z comma a, y should be equal to z here. So the number of columns in A should be same as the number of rows in B. So y should be equal to z. And then the final matrix, as I said, the multiplicative of these becomes x by a. So it'll have x rows and e columns. That's how these numbers work together, or that's how the shapes play out when you are trying to multiply two matrices, which is also why you cannot multiply any matrix. So I was trying to show that not necessarily is the multiplicative of AB equal to BA, but even before that, I ran into an error which says that no, it's not possible to multiply these because these have a different shape as to what's expected. Ishan is talking about transposes. So transposes, and thanks for that, Ishan, can be thought of taking a rotation in geometric space. Thanks for that comment. What is art in Python? So I went to Stack Overflow to learn about the origins of that, but it comes from when you write matrices. It's the product of them inside Python. So when you actually call the, and if you'll exclude, please excuse my terrible writing, but add function comes from the word matrices, and that's where the add function comes from. It's basically denoting the multiplicate of these two. The thing I was trying to point out earlier is when you're working with NumPy arrays, it behaves differently to how it behaves inside Python. And that's one thing to be careful about. So what I would encourage you to do after this live stream, or maybe it's super clear to you, is check out all of these functions, which is at star np.matmul and np.multiply, and see how they behave differently, and see np.dot, how does that behave. So I'm skipping the definition of dot product, but let's quickly cover that for anyone who's new here. This is one way to denote matrix multiplication. So if C is the product of A and B, the ith and jth element of C can be written like so. So this is just a simple multiplication between these individual numbers. So the number at the ith row and kth column for A multiplied by the kth, the number in the kth row and jth column in B, and all of these summed together become the I comma j element for C. For me, at least, it takes me more time to digest this compared to this, which is why I'm trying to switch between these two and trying to stay focused here more and more, because I eventually you'll be doing this more than that, right? And whenever you come across a paper covering these, try to think of this. Again, a strong opinion here. um Element-wise product is also known as Hadamard product, and is denoted like so. The dot product between two vectors is the matrix product of X transpose with Y. So after this, we'll learn about identity and inverse matrices. And these can be written like so. So the claim here is, if you multiply a matrix by itself, you get an identity matrix. So using that claim, what I did was I said, okay, NumPy, let's take the invert of A and let's multiply that with A. And is that equal to an identity matrix of the shape A? It says no, it's not true, and it actually complains and when I'm calling invert function. That happens because you don't use np.invert to calculate the inverse. In fact, you call np.linalg.inv to calculate the inverse of a matrix. So when I actually do that, it still isn't the same as an identity matrix created like so. Why is that? Because I've initialized A with random numbers. And if you actually do that, so I'm not going to print that out. Try that. And you'll see that it's actually floating point numbers. And the thing about that is, it's not an accurate multiplication when you do that, right? So you call np.allClose, which returns true if two arrays equal within a tolerance. So if they are very close to each other, this should return true. And for this case, it will give me true. Remember, you can also check the function definitions inside Jupyter Notebook by putting a question mark there or by pressing Shift Tab. So when I call np.allClose along this, it'll give me true uh, as a statement, as a answer, which means that this is not a perfect inverse, right? Because it's not exactly an identity matrix, and if you print that out, you'll see that. And that's because later in the book you'll see that not all inverses exist, and that's why something known as a pseudo inverse exists, which is the closest thing to an inverse. And you can call that by np dot np.linalg dot pinv, which computes the Moore Penrose pseudo inverse of a matrix. But an identity matrix, which would be the multiplicative of an inverse of a matrix with itself, can be shown like so. So it has 1 alongside the diagonal and zeros alongside every other element. Do I have a symbol chart for the math equations? If you actually check the first chapter of the book, you should be able to see all of them. Let's see if I can quickly point you to that. Somewhere, I think, somewhere in this chapter it's mentioned. sorry, not this chapter. It's in notations. So if you actually go to the book's website, just go to the notation chapter, and you will be able to see all of these. So I'm also skipping sets and their dimensions, minute things inside the book, but they're pretty clear there. So I assume it should be obvious to everyone. But if you want me to cover that, just let me know. So I'm only highlighting things that are, in my opinion, worth quickly covering in this live stream. Again, I would expect everyone to actually read the chapter before or after this. So it's a study group and not a lecture. It's not a replacement for the book. As a reminder, um, the thing after inverse and identity matrices in the book is linear dependence and span. So the authors claim for A inverse to exist, there must be exactly one solution for every value of B for this equation. Um, and actually, let's read that inside the book because that's more easy. So in order for the system Ax equal to B to have a solution, there must be exactly one solution for every value of B is claimed inside this para. And the span, sorry, I'm trying to find the particular paragraph. The span of a set of vectors is the set of all points obtainable by a linear combination of the original vectors. So determining whether Ax equal to B has a solution amounts to testing whether B is in the span of the columns of A. And this particular span is known as the column space or range of A. Note this is slightly different from the range used in Python, so please don't confuse it with that. Do I have all of this memorized by heart? No, I don't. And as you can see, I'm still trying to find the book. So I have my physical book with the notes here, and that's what I'm trying to point out. Um, I don't think I'll be able to memorize all of this. The next thing I want to point out is linear dependence. So a set of vectors is linearly dependent if no vector in the set is a linear combination of the other vectors. So if we add a vector to a set that is a linear combination of the other vectors, the new vector does not add any points to the set span. And a square matrix with linearly dependent columns is known as a singular matrix. So I'm glancing over a lot of definitions here, but I'm only pointing out the ones I think that are important. Uh, Easy says hi. Hey, Easy. So all of this was to solve the equation and derive a few definitions around Ax is equal to B, which would represent a collection of lines. So this all of these definitions are around Ax is equal to B, and these definitions are being used to define the span and linear independence and how you can solve or how you cannot solve these equations. So sometimes you need to measure the size of a vector, and in machine learning, this is done by using a function called a norm. LP norm is defined like so. So it's the sum of all numbers inside x, or all elements of vector x to the power p. And after you calculate all of this sum, you raise it to the power 1 by p. So if p was 2 here, you would add all of these squares and then take a square root. These are functions mapping vectors to non-negative values. And intuitively, the norm of vector x measures the distance from the origin to the point x. After this, there are some mathematical definitions which I'll skip. For L2 norm, p equals to 2. So what I just described, where you take the square root of the sum of squares, it's known as the Euclidean norm, which is the Euclidean distance from the origin to the point identified by x. And L2 norm is so frequently used in machine learning that it is often denoted like so. So double modulus of x. You can also measure the size of a vector using squared L2 norm, which can simply be calculated by the transpose multiplied by the vector itself. After this, the authors talk about when you're working with negative values or smaller values, it's also ideal to work with the L1 norm. And they then define that L1 norm can simply be the sum of all elements inside a vector. L1 norm is commonly used when the difference between 0 and non-zero elements is very important. And every time an element of x moves from 0 by a small number, L1 norm increases by that number. You can also have something known as a max norm. So this norm simplifies to the absolute value of the element with the largest magnitude. Basically, it returns the largest number inside the vector. Sometimes you also may wish to work or measure the size of a matrix. And the most common way to do this is with the Frobenius norm, which is denoted like so with a subscript f. And here you take the square root of the sum of squares of all elements. And this, if you're paying attention, is the same as L2 norm of a vector. So how do you do that? All of this inside NumPy. It's simply one function. And as I said, I'll switch to more theory towards the later half, and we're already at the later half of the chapter. But it's simply a norm function inside linalg. And when you call that, you can see that you can pass on different hyperparameters here, which will return different norms. So a norm is used to measure the size of a vector, as I said earlier. Ishan has some great comments today. I'll quickly come to Ishan's comment. Before that, isn't L1 norm better for higher dimensional data compared to L2? I'll have to double check this. I'm not sure about this question. Sorry about that. Although L2 norm is more computationally expensive, if that's what you're pointing to. To understand linear dependence, one can think of a column in a matrix as a road to a destination. And if two columns have the same destination, one of them contributes to nothing in terms of the destination. That's a better description. Thanks, Ishan. The destination is basically the coordinate system in this case, right? So every element is a coordinate in the x comma y space if you're working with two-dimensional data, I think. Next, it's worth to cover some special kinds of matrices. And inside the book, this is accompanied with a lot of definitions that I'm skipping over. But you could have a diagonal matrix where the elements, all the elements except the diagonal are 0. A special case of this is the identity matrix, where all the numbers alongside a diagonal are 1. You could also have a function like so, or a matrix like so that has all ones. There's no special name for this. You just call np dot ones to create this. The property of this would be when you multiply this with any sorry, it's not true. I was going to say when you multiply this with a vector, it will give the same number, but that might not be necessarily true. So sorry about that. Um, when you multiply with a scalar one, you'd get the same number, not with the one matrix. Yeah, I was just confusing myself. Anupam says L2 norm is more sensitive to outliers. Could you share where we can find the discussion forums? They're in the description. So if you just click on the description of this video, you can find a link to the forums. An identity matrix, as I said earlier, has all numbers alongside the diagonal to be 1 and everything else is 0. And you can print out the diagonal by calling np.diag, which returns the diagonal of this matrix, which is 1 comma 1 comma 1. For a symmetric matrix, A is equal to A transpose, and I can actually switch to the book because it's formatted better there. A symmetric matrix is any matrix that is equal to its own transpose, like so. And symmetric matrices often arise when the entries are generated by some function of two arguments that does not depend on the order of arguments. For example, A is a matrix of distance measurements. A I comma j giving the distance from point I to j. In this case, since the distance from I to j would remain the same no matter the order, right? A I comma j would be equal to A j comma I. A unit vector is a vector with a unit norm. So it's the thing I wanted to also highlight here is when you call ones, it's not the same as a unit vector. It just np.1 simply creates an array of given shape and type filled with ones. A vector x and y are orthogonal to each other if the transpose of x multiplied by y is equal to 0. If both the vectors have a non-zero norm, this would mean that they are at 90-degree angle to each other. And inside of real numbers, most n vectors may be mutually orthogonal with non-zero norms. If the vectors are not only orthogonal but also have a unit norm, we call them orthonormal. An orthogonal matrix is a square matrix whose rows are mutually orthonormal and whose columns are mutually orthonormal as well. So the transpose of A multiplied by A can be written like so. And this would give you an identity matrix, which would mean the inverse is the same as the transpose. Because when you multiply with an inverse, that should give you an identity matrix. And if the transpose being multiplied with the matrix is giving you that, that means the inverse can be written as a transpose. Okay, let me catch up with the questions real quick. Is the linear algebra part going to be essential for interpreting this book? Not really. So it's also like it's somewhat relevant to papers, right? Like so for me, the end goal is to hopefully be faster at reading the mathematical bits in papers. And is this going to help with that? Yes, whenever linear algebra is being used in the papers, right? So for me, as you can see, I slow down when I'm going through the definitions myself, because for me, I'm more used to all of this compared to these definitions, right? So what really matters is for me how you call them inside NumPy, and then just having a broad understanding of what this means. So I would know that what is orthogonal, what is unit vector, what is orthonormal. Maybe I'll forget orthonormal and I'll have to go back to the book. But it's better for me if I know how to call that function inside NumPy or PyTorch, how to basically replicate that. Do we need to cover Thomas Calculus or some rigorous book? I'm not sure of that book, but no, I would just say for any resource, just focus on the like least effort path, right? So just read this book and then just like get to wherever you want to work towards. We can take up algebra loaded technical paper. If you can find one, I'm happy to do that. But that's why I suggested like a better exercise would just be translating this chapter into NumPy inside a Jupyter notebook. I mean, I'm not like taking credit for that. It's just the book we're taking and translating that into Python, right? But that's also what's missing somewhat in the book. So if you actually go to the website, and let me go to the original page, you'll see that there's an exercises tab as well. But this just has linear algebra, and after that, other exercises weren't really added. So like if you actually go through the effort of reading through this, you're welcome to contribute. Sorry, I wasn't sharing my screen. But what I've done is what I've done here is I've just gone to the exercises tab inside the book, and it only has linear algebra here, right? So maybe you can actually contribute to the book by creating these examples. So that's why I created the repository which I mentioned. I'll push this notebook after the live stream to that. Again, it's the top link in the description. But you're welcome to do whatever. That's only my suggestion and my bias that I'm bringing to this live stream. Um, okay. So for eigen decomposition, it's defined like so. Whenever you're taking a number and breaking it down into its prime attribute, so the prime numbers that make it up, right? That helps you understand the properties of this number. So we can say this is an even number because it's divisible by 2, and it's also divisible by 3. So that'll tell us some properties of this number, right? Um, Similarly, when you're working with matrices, you can do eigen decomposition, in which we decompose a matrix into a set of eigenvectors and values. An eigenvector of a square matrix A is so when you multiply A with V, it gives you lambda V, and lambda is the eigenvalue corresponding to this eigenvector. You can also have left eigenvalues defined like so. So you take the transpose and uh, move V to the left side of A. That's how I remember it. But the authors say we are usually concerned with right eigenvectors. After this, they defined how the eigen decomposition of A can be represented. If your matrix has n linearly independent eigenvectors, you can represent it like so. If you actually want to calculate these inside NumPy, you can simply call np.linal.eig, and that'll give you both the eigenvalues and the eigenvectors. So again, go to the documentation, read up about this function. And the thing that really helped me was going to these examples over and over again. So instead of even, I would say, reading this, just scroll down to all of these examples, and they'll make more and more sense as you start going through all of these terms for me. Prabha says they did have a reading group when the book launched. I think you're referring to this one, right? Let me quickly find it. So it's still there on YouTube, and my only critique there is it doesn't have enough Python in there. If you actually go to YouTube and just search deep learning book, you'll find my video, and you'll also find these set of videos by the original author Ian Goodfellow and different people covering bits and pieces. But for me, what I'm trying to bridge is the gap between exercise and different things for all study groups. So I'm not sure if that's your end goal. If it's just covering the theory, you're also welcome to watch the other reading group. But I have watched those lectures, and I'm only trying to add value where I think it's missing. So that's my short pitch for why I'm still doing this. And here's another way of effect of eigen vectors and eigen values being visualized. So if you read the subscript, this is an example of the effect of eigenvectors and values. We have a matrix A with two orthonormal eigenvectors, V1 with eigenvalues lambda 1 and V2 with eigenvalues lambda 2. We plot all set of unit vectors as a unit circle, and we plot the set of all points AU. So when you multiply it with the eigenvalues and eigenvectors, you can see it distorts the circle like so. Now, why is this helpful at all? This is transforming the matrix, right, in a way. So similar to when you like calculating prime factors of a number, this is somewhat helpful in understanding the matrix, as I understand. So it's just a form of a transform, and it's a form of breaking down matrix into its components, if I may. There are a few more definitions here about a matrix which is positive definite, positive semi definite, so on and so forth. I tried to remember these. Actually, in my notebook I had questions to see if I've been able to memorize this. I couldn't. So my assumption is it's best to just read through it once, and whenever you see this term pop up anywhere, you would know which chapter to go back to, or you can just go to the glossary and find it asap. So for me, I've not found a place yet where I need to remember this exactly. So I know we're supposed to read this book. I would say try to understand this more than memorize it. And whenever it's required, you can always go back to this chapter. After this, they talk about singular value decomposition, also known as SVD. And again, one more thing I want to quickly point out here is there's a very long definition here, but what's worth remembering is it's just a .svd function inside numpy. So whenever you see singular value decomposition being mentioned in a paper, you can simply in your head replace it with np.lineal.svd, right? So the singular value decomposition provides another way to factorize a matrix into singular vectors and singular values. This enables us to discover some of the same kind of information. However, SVD is more generally applicable. Every real matrix has a singular value decomposition, but the same is not true for eigenvalue decomposition. And later on, they define why this is true. But again, key thing to remember, every matrix has a SVD, but not necessarily an eigenvalue decomposition. Finally, I have two more topics after this, so this is not the final one. Uh, Matrix inversion is not defined for matrices that are not square. And suppose that you still want to calculate it, you can call the pseudo inverse, which is defined like so. The thing to point out here is alpha is close to 0, which means that this entire term can be thought of 0. or this entire term becomes, sorry, alpha here can be thought of a very small number multiplier with I. So it's a very small number being added to what should be the inverse of it, right? And the pseudo inverse is denoted by a plus. So practical algorithms are defined like so. This is the mathematical definition, but they're defined like so, where D and V are the SVD of A. And how do you actually call that? Again, it's simply a function inside NumPy, as I mentioned earlier. So again, for me, I've been struggling a lot. Like I would go back and read this repeatedly, and I would really not understand should I remember the definition or not. So for me, I've only created like memory associations with all of these things. Uh, I would say definitely read through it once, but for me, I've not tried to memorize all of these. After this, we talk about the trace operator, and the trace operator gives the sum of all diagonal entries inside a matrix. It's useful for a variety of reasons. They say some operations that are difficult to specify without resorting to summation can be specified using matrix products and trace operators. And then they've specified a few examples where it's useful. In NumPy, you simply call np.trace. It's not np.lin_al.trace, it's np.trace. The determinant of a square matrix, denoted as DETA, is a function that maps maps matrices to real scalars, and the determinant is equal to the product of all eigenvalues of the matrix. So the determinant is basically the product of eigenvalues of the matrix. The absolute value of this is a measure of how much multiplication by the matrix, sorry, how much the matrix expands or contracts if you multiply it. So if the determinant is 0, then the space is contracted completely, at least along one dimension. If it's 1, then the transformation preserves the volume. Inside NumPy, it's a function in lin_alg where you called it. After this, the authors cover PCA. Again, I have read through this, but for me, it's quite mathematically dense. So I actually wrote down a few examples and calculated all of this. In practice, you just call a PCA function inside scikit-learn. But if you're working through this, it might be worth actually writing down examples. So what I like to do is come up with very simple matrices where you'd work through these examples. Spend more time in NumPy docs and PyTorch docs. If you struggle with the math, I would say again, I'm repeating this many times because again, like the key thing to remember here is you only have so many hours, right? So if it's like taking more than 3 hours to understand PCA, either look for a better explainer. For me, I struggle with like the math heavy notations, right? Go to docs or like try to find a practical example that helps you associate it in memory. uh Muhammad says I struggle with the book as much as he does, so we both can he relates to my struggle. I think is what he's trying to say. Is that the thing? Is the thing behind me ML rig? Yes, it is. The determinant is basically the amount of area covered by a matrix in geometric space. That makes sense. Thanks for explaining that. But again, like I'm curious where is a use case where you'd have to actually remember this, right? Unless you're like creating a new algorithm, you probably won't. So for me, it's a determinant is inside NumPy lin_alg.det. I don't know if Ishan agrees with my my way of remembering things. Um, okay, I don't see any other questions, so I'll quickly wrap up. Here's some suggested homework, and let me switch to the slides, which are gone now. Let me bring those up again. I would say familiarize yourself again. I'm saying this with NumPy docs. Spend more time exploring np.linalg. It's a subset of the NumPy API, but that contains all of the linear algebraic functions. And there's quite a few of these. So just spend more time going through these examples. Um, Try to apply this knowledge to PyTorch. And you're welcome to contribute to the community repo as well, which again I've linked there, and I'll probably push this notebook with some more cleaning up. So I'd ideally like to have more text elaborating on this. So I'll try to push this notebook today or tomorrow, and you all are welcome to help improve this. So I hope this becomes a community effort. But that's it for this chapter. So quickly scrolling up, here's what we covered in this live stream. And you can expect a similar taste for all of the future ones, right? Where I try to explain things at a abstract level and then also point out the Pythonic meaning behind them. So the chapter after this is, I can share my screen and point you to it. The chapter after this is probability and information theory. So we'll go in order and cover the first 11 chapters or first 10 chapters. But that's all. For contributions, Ishan, you can just help polish the notebook. So what I want to do is like create a supplementary Pythonic repository for the book. I don't know if that makes sense at all. um, okay, thanks for watching, everyone. We'll meet again next week and we'll read the third chapter, or I'll summarize the third chapter with hopefully a more polished notebook. Apologies if today we didn't have enough text in the notebook. I only wrote this in like an hour or so. Um, if you watch this video, consider leaving a like and subscribing. And I'll also have a live stream tomorrow. So every Sundays I live stream Kaggle Top Solutions if you're into that. And every Saturdays we'll be going through this book as long as there's interest. Did you find any other blogs which helped you covering fundamentals? I would just look up stuff. So I like for the actually forgot about the NumPy nuances. So I went to Stack Overflow and that led me to a bunch of blog posts that were linked there. So that's what I did. I'll wait for Anupam's last question before wrapping up. Using Gilbert Strang's lecture videos for any concepts that you find difficult. These are very good explainers. Thanks for that, Balaji. I'll try to watch them myself, and if I find any better explainers, I'll try to like cover those in the next week again. How many hours do you spend on data science? Would you consider this data science, or would you consider only Kaggle data science, or would you consider only deep learning data science? I don't know. I spend time doing stuff I enjoy. So my path is just optimizing everything, optimizing my life for doing things that I enjoy. So that's what I mostly spend my days doing. It involves Call of Duty and whatnot also here and there, but that's how I spend my hours. Okay, awesome. Thanks everyone for joining. I'll wrap this up here. I'll see you all next week. Thanks for watching.